So, did you think about the question that I asked yesterday? So, take A to be kxy and take in for each n in n, there exists an ideal in A which is generated by n elements. So, when I say generated by, I mean minimally generated by, because otherwise you can add many elements to the generating set which is minimally did you think about this question? Okay, so I will still leave this as an exercise. So, what we are going to see is that this does not really say that ideals of kxy is not finitely generated. So, this is famous theorem of Hilbert. This is called Hilbert basis theorem. Hilbert did not prove this in this did not state the result in this manner or prove this like this. He was studying rings of invariance, and he wanted to prove that it is a finitely generated K algebra. So, but the idea was used later to prove something like this. So, the statement is, if A is Noetherian, then so is A x, where x is an indeterminate over A. Okay. That is, A x is also Noetherian. Okay. So, you want to prove that every ideal of A x is finitely generated. Suppose there exists an ideal which is not finitely generated. Okay. There exists an ideal I in A x which is not finitely generated. Okay. We want to arrive at a contradiction. Okay. So, what we do is, see, we want to make use of the fact that A is Noetherian. Okay. So, let I mean set I naught equal to 0. Okay. Then let f1 in I be a polynomial in I of least degree. If I take this collection of all elements in I and look at the degrees of each polynomial, that will be a subset of set of all natural numbers. That always set of all natural numbers always have a least element. So, take a least element and look at a polynomial corresponding to that. Okay. And let I1 be the ideal generated by F1. Okay. Now, let F2 be an element of least degree in I without the ideal generated by F1. Okay. And I2 be the ideal generated by F1 and F2. Keep doing this recursively. Let Fi be a polynomial in I without F1 up to Fi minus 1, ideal generated by F1 up to Fi minus 1, which is of a polynomial of least degree in the set. Okay. So, first thing that you can observe is that degree of F1 is less than or equal to degree of F2 less than or equal to degree of F3 and so on. That is one observation. Okay. Another observation is I1 contained in I2 contained in I3 and so on. Okay. Now, we want to say that so let us look at, let Ai be the leading coefficient of Fi. See, from here we have to obtain some ideal in A and use the fact that the ideal there is finitely generated, okay, and consider let Ji be the ideal generated by A1 up to Ai. Okay. Then again, of course, you have ideal generated by J1 contained in J2 and so on. This chain is happening in A, and A is Noetherian, which means this terminates at some point. Okay. Since this is a chain of ideals in A, there exists n such that Jn is equal to Jn plus 1 and so on. Okay. Which means that this element a n plus 1, which is the leading coefficient of f n plus 1, it belongs to J n, or in other words I can write this as summation R I A I from 1 to n for some R I in A. Okay. Now, let f be equal to f n plus 1 minus summation R I f I from 1 to n. Okay. Now what can you say about this? Degree of f will be degree of f is strictly less than degree of f n plus 1. Right. What does that mean? See, how did I now look at this element f? F is in I n plus 1, right. F is in I n plus 1 because it is a linear combination of f 1 up to f n plus 1. F n plus 1 was chosen as an element in I 1 up to I mean I without f 1 up to f n of least degree. F is in I n plus 1 and degree is less than degree of f n plus 1. That means f has to be in I n. But if f is in I n, I can write f n plus 1 as linear combination of f and this, which means f n plus 1 is in I n. That is a contradiction. Okay. Since f is in I n plus 1, this implies that degree of f is strictly less than f n plus 1 and f is in I n plus 1 implies that f is in I n, because since this and f is in I n plus 1 implies f is in I n, since f n plus 1 is a polynomial of least degree in I without f 1 up to f n. So therefore f is in I n implies f n plus 1 is in I n, and that is a contradiction. Because f n plus 1 is chosen to be in I, the complement of I n in I n plus in I. So therefore that is a contradiction. So what does that contradiction say? That our assumption that we have made that the ideal I is not finitely generated is wrong, which means I is finitely generated, and that implies A x is Noetherian. Okay. There is a proof given in Athia MacDonald which is a constructive proof from so starting with an ideal I in A x, one constructs a generating set. Okay, it is like an algorithm. You look at for each n, construct an ideal in A and use the fact that ideals of A are finitely generated to get a generating set, finite generating set for I in A x. Okay. So do go through the proof and try to understand that. That is slightly lengthier, but it is a constructive proof. It gives a concrete generating set for a given ideal in A x. Okay. So that is also a nice proof. This is, but that is more slightly more lengthy, and it's techniques are similar, but it is slightly more lengthy and a constructive proof. So, do go through that proof as well. Okay. So, this says that kxy is Noetherian. In kxy there exists, given any n, there exists an ideal which is generated, minimally generated by n elements, but there are no elements which are infinitely generated. Okay. However large n is, every ideal is finitely generated. Okay. This is again I can give you in for each n, but try to construct on your own, try to see if you can construct. I can even give you a hint saying that you can think of ideals generated by monomials. What are monomials? Polynomial is a sum of monomials. So, a monomial in polynomial ring is of the form x1 power alpha 1 up to xn power alpha n. So, here it will be some x power a y power b. Try to think of ideals generated by monomials. Okay. So, yes. So, this says that every polynomial ring with finitely many variables is a polynomial, is Noetherian. So, if A is Noetherian, then so is more generally, if A is Noetherian, then so is any finitely generated A algebra. How does any finitely generated A algebra look like? Quotient of A x1 up to xn. So, if A is Noetherian, this is Noetherian, therefore, any quotient is Noetherian, therefore, any finitely generated A algebra is Noetherian. Okay. This is a very important result that goes into finite generation of ideals in polynomial ring is something that is one of the most basic thing required in algebraic geometry, because when we are considering a set in Kn and look at all the polynomials which vanish on all the points, okay, all the polynomials whose zeros are this given set, this there will be infinitely many polynomials, but when we have to look at the properties, we only have to look at only finitely many of them, the generating set. Okay, it's so there are I mean this is something that is very basic required in algebraic geometry. So, this says that Noetherian rings are kind of special, okay, they are nice. See, we in Z, okay, in Z or even in any UFD. So, let us, when we wanted to talk about analogues, we always start with Z. In Z, if you take any integer n, okay, I can write this as p1 power alpha 1 up to pn power alpha n, where p1 p2 up to pn are sorry, okay, so p r alpha r, they are different distinct primes, okay. that means it has a unique prime decomposition. Okay. Now the question is how far we can push this. Okay. So one thing, like say if I look at the ideal generated by n, I can write this as ideal generated by p1 power alpha 1 times ideal generated by p2 power alpha 2 ideal generated by pr power alpha r. These are not prime ideals, right. The ideal is not a prime ideal. If alpha 1 is bigger than 2, bigger than or equal to 2, this ideal will not be a prime ideal, but it is, its radical is a prime ideal, right. So in general in Noetherian rings there is what is called a primary decomposition. Okay. So let us look at what is meant by primary decomposition. Let us begin with definition of primary ideals. This is, for the definition of primary ideals and so on, we do not need any Noetherianness. When it is Noetherian, things are much more nice. Many properties are nice when the ring is Noetherian. So let us start with a commutative ring, A be a commutative ring. Did we define a primary ideal earlier? No. Okay. An ideal, proper ideal A is said to be a primary ideal if so I is said to be a prime ideal if x y is in I implies either x is in I or y is in I. Equivalently, A mod I is an integral domain, right. So here we say this is said to be a primary ideal if for x comma y in A, x y is in I implies either x is in I or a power of y is in I. Or in other words, if a product is in I and one of them is not in I, the other one need not be in I, but some power of this belongs to I. This will be more clear if you look at the equivalent statement. This is equivalently, if I look at A mod I, okay, if I look at A mod I, x y is in I, if you translate into A mod I, it says x bar y bar is 0, x bar y bar is 0 and suppose x is not in, that means y is a non-zero divisor in A mod I. If it is a non-zero divisor, that means there exists some x with not in I such that x bar y bar is 0, but then in that case this should be true, that means y bar power n should be 0, that means every non-zero divisor is a nilpotent. Y will be a non-zero divisor, right. If I assume that x y is in I and x is not in I, implies y power n is in I for some n.
So is this condition equivalent to xy belongs to I implies either some power of x belongs to I or some power of y?
I mean these two are
Yeah, but equivalent as in if some power of x or some power of y belongs to I,
yeah.
then if we take suppose some power of y does not belong to I, then this says that x should belong to y, not.
So see, that is what here x and y, they do not really distinguish between each other, right. I mean x y is same as y x, so you can switch the roles of x and y. I mean what it says is that if there is a product with, you know, if there is a product with one of them not in I, then some power of the other element should be in I. Okay, that is exactly what what we are seeing in the equivalent form here, that when do you say x y is in I with one of them not in I, which means we have x bar y bar is 0 with x bar non-zero, that means y bar is a 0 divisor, it is a 0 divisor in A mod I. But then the conclusion is that it should be nilpotent, y n is in should be in I, or in other words y bar power n should be 0, that means y bar is nilpotent in A mod I, or in other words the equivalent form is every non-zero 0 divisor is nilpotent, right. Every, I mean 0 is also of course every 0 divisor is nilpotent in A mod I. So can you give me a first example of a primary ideal? Can you give me an example of a, yeah, in Z, or you know slightly in general. Okay, so let me write this. So example, p power n in Z. Why is this primary? How do you justify this?
If someone is p power n, then p power n should divide it.
If x y belongs to the ideal generated by p power n, that means p power n, so x y will be of the form some m times p power n. That means p divides either x or y. So if x is not in p power n, that means p cannot divide, p power n does not divide x. So p will divide, yeah, p power n has to divide y in this case, some power of p, p has to divide y. Okay. If x is not in p power n, then p divides y. Because p power n is on the right hand side, so that much power, at least that much power of p should be there in this product. P power n is not there in x, so therefore some p will be there in the prime decomposition of y. That means p divides y, and that would imply that y power n will be in p power n. At least there could be some smaller power there, but y power n has to be. Now can you read this line once again and give me an example of a primary ideal in general? So no, I just start with a commutative ring A. What if there are no zero divisors? Yeah, you said something? It is true. If the ideal is maximal, slightly more general, if it is a prime ideal, right? If ideal is prime, then there are no non-zero zero divisors. So this is vacuously true. For that ideal, any prime ideal, if xy is in I, that will imply either x is in I or y is in I. So therefore this is true with n equal to 1. So therefore every prime ideal is a prime ideal is primary. Okay. Yeah.
If xy belongs to I, then xy y bar is equal to 0 in A mod I.
Sorry.
If xy belongs to I, then x bar y bar is equal to 0 in A mod I.
Yeah.
But A mod I is integral domain.
Yeah.
So
X
x bar is not 0, then
Y bar has to be 0. That means y is in I if I is prime, right? You are talking about I being prime.
we should imply that reversing y power n should belong to A.
For some n, right? So for n equal to 1, this is true. If yeah.
What about power of prime ideal?
Yeah. So the question is, if I take p power n, in general I take p power n, is this primary? So there is this example which says that I will come back to this. This question makes sense. I mean it is slightly more interesting after we prove one basic result, that if I is primary, then radical of I is the smallest prime containing I. Okay. This is see, we know that radical of I is prime ideal. Yeah. We know that radical of I is equal to intersection of prime ideal P prime, right? We are saying that if I is primary, you can pin down to one prime ideal which is the smallest one which contains I. Okay. So let's look at x y be in the radical of I. that means some power x n power x n y n belongs to I by definition of radical. Now I is primary, that means either x power n belongs to I, okay, x power n belongs to I, or y power m y power n whole power some m belongs to I for some m. What does that say? X belongs to radical of I, or y belongs to radical of I, right. Y power n whole power m is same as some power of y. Some power of y belongs to I means y is in the radical. So what we have shown is that x y is in the radical implies either x is in the radical or y is in the radical, which means radical of I is a prime ideal. And by definition it has to be the smallest prime ideal. The smallest prime ideal. So if I is primary, the radical is prime. So now let us look at this question. Pn, this is an ideal with whose radical is p. So this question asks if the converse of this is true, that the radical is a prime ideal, can we say that I is primary or not? Unfortunately this is not true. Look at this ring A equal to k x y z mod x y minus z square, and look at I equal to x z x bar z bar in A. Then this is a prime ideal in A. Why is it a prime ideal? What is A mod I? See, this is an ideal containing this, right, call this J. Then what is A mod I? A mod I is k x y z mod j modulo x z mod j, which is isomorphic to k x y z mod x z, and this is isomorphic to k y. This is an integral domain. So therefore this is a I is a prime ideal in A, right. Now let us look at I square. What happens to I square? Can you write down what is I square? I square is the ideal generated by I square is the ideal generated by x square x bar square x bar z bar and z bar square. But now in A, what is z bar square? Z bar square is same as z bar square is same as x bar y bar, right. X bar y bar minus z bar square is 0 in A. So, therefore, x bar y bar and z bar square is same as x bar y bar. So, this means that x bar square x bar y bar belongs to I square. Right, and x bar is not an I square. For this to be a primary ideal, some power of y should be in I square. Do we have that? Right. So, x bar is not an I square, and y bar power n is also not an I square for any n. So, that implies that I square. So, here I should first remark that I is a prime ideal in A. So, this is not a primary ideal. I is a prime ideal, but I square is not a primary ideal. So, power of prime need not be a primary ideal. Is that clear? If you take a prime ideal and look at its powers, that need not be a primary ideal. In the case of Z, it is true, but in general that is not true. In Z, primary ideals are precisely the ideals which are product of powers of prime ideals. I be an ideal such that a radical of I is maximal. Okay. Now, radical of I is a prime ideal need not necessarily imply that I is primary. Suppose your radical is a maximal ideal. Yeah. Can we say I is primary? Let us look at A mod I. Okay. What are the ideals of A mod I? Ideals containing I, J mod I, where J is an ideal containing. What are the prime ideals of A mod I? Prime ideals of A containing I. Now, radical of I, what is radical of I? It is by definition or characterization, it is the intersection of all prime ideals containing I, and that is a maximal ideal, right. Intersection of all prime ideals containing I is a maximal ideal. Therefore, the only prime ideal containing I is the maximal ideal, which is the radical of I. That is the only prime ideal containing I, right. So, radical of I is the only prime ideal containing I. That means A mod I is a local ring with unique maximal ideal M mod I. What does that say? All the elements, look at the elements of A mod I. Either they are units or they are in M mod I. So, this implies A mod I is a local ring with unique maximal ideal M mod I. So, what is M here? I will call this M. So, elements of A mod I, either they are in M mod I or in the complement of M mod I. If it is not in M mod I, it is a unit. If it is in M mod I, it means that x bar belongs to M, which is the radical of I. So, that means some power of that belongs to I, which means x bar power n is 0. That means every non-unit is nilpotent. Now, the equivalent statement for primary ideal says that every 0 divisor is nilpotent. Here we are proving that every non-unit is nilpotent. Non-unit cannot be a unit cannot be a 0 divisor. So, anything that is not 0 divisor is nilpotent here. In particular, every non-zero divisor is every 0 divisor is nilpotent. Therefore, this is ideal I is primary ideal. Okay. So, let me write this down. This implies every non-unit element of A mod I is in M mod I. If x bar belongs to M mod I, that means x bar belongs to radical of I mod I, which means x bar power n belongs to x power n belongs to I. That means x bar power n is 0, which means every non-unit in A mod I is nilpotent. And that implies that I is a primary ideal. So, what we have proved here is then I is primary. Okay. Radical of I is a prime ideal does not imply that I is primary, but what we are proving here is that if the radical is a maximal ideal, then yes, the ideal is a primary ideal. Now, we will continue with so in the case of Z we can say that it is like a primary decomposition. You take an ideal nz, it is like a decomposition into a primary ideals. We will see such a similar decomposition in the case of Noetherian rings.